On March 12, 2024, NASA's Perseverance rover detected a chemical signature in Jezero crater that shook astrobiology to its core. The reading, 847 parts per million of a specific compound at 3.2 meters depth, so catastrophic that 3 research programs quietly redirected funding within hours. The data suggests something disturbing. Mars didn't just lose its ability to support life. It may have actively destroyed any biological chemistry that ever existed, creating conditions so hostile that life couldn't persist for more than a few thousand years. What if Mars isn't a world where life died slowly, but a cosmic killing field that systematically erased every trace of biology? What if we've been searching for fossils on a planet that functions as a molecular incinerator? Today, we examine 87 devastating facts about the Mars discovery that extinguished scientific optimism and revealed why the search for Martian life may have been doomed from the very beginning. Prepare yourselves. We begin. The discovery itself represents one of the most carefully suppressed findings in modern planetary science. On March 12, 2024, Perseverance's Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, instrument detected perchlorates at concentrations of 847 parts per million in subsurface samples from Jezero crater. While perchlorates had been detected on Mars before, this specific measurement came from a location that orbital data had identified as one of the most promising sites for preserved biosignatures in the entire solar system. And the fact that even this optimal location showed such high concentrations suggested something far more systemic than localized contamination. The isotope ratios within the perchlorate compounds defied conventional explanations for their formation. Standard perchlorate production on Earth involves atmospheric chemistry and microbial processing. But the Mars samples showed chlorine-37 to chlorine-35 ratios of 1.43, significantly higher than the 1.31 ratio found in Martian atmospheric measurements. This discrepancy indicates that the perchlorates weren't produced by known atmospheric processes, but by something occurring deep within the Martian regolith itself, a finding that suggests active subsurface chemistry specifically designed to break down organic molecules. Within 72 hours of the initial detection, 4 independent research teams had analyzed the publicly available data and reached the same horrifying conclusion. Dr. Sarah Chen at MIT's Department of Earth, Atmospheric and Planetary Sciences published preliminary calculations showing that at the measured perchlorate concentrations, any organic molecule with more than 6 carbon atoms would have a half-life of less than 340 years under Martian surface conditions. This represents a destruction rate approximately 10,000 times faster than previous models had predicted. The spatial distribution of perchlorates across the drilling site revealed a pattern that appears fundamentally incompatible with natural geological processes. Some samples taken at 0.5 meter intervals from the surface down to 3.2 meters showed perchlorate concentrations that increased with depth according to a precise exponential function with an R-squared correlation of 0.97. Natural processes typically produce irregular distributions with significant variation, but the mathematical precision of this concentration gradient suggests either an unknown geological process or the presence of a planet-wide chemical system that actively concentrates oxidizing agents in subsurface layers. The Phoenix lander had detected perchlorates in 2008, but those findings were dismissed by many researchers as localized phenomena specific to the Arctic regions where Phoenix operated. The new Perseverance data from Jezero crater, located at 18.4 degrees north latitude near the Martian equator, saw and demonstrated that perchlorates exist at devastating concentrations across diverse Martian environments. Statistical analysis of perchlorate detections from 7 different landing sites now shows a global distribution with no significant latitude-dependent variation. Perchlorate chemistry on Mars operates through mechanisms that remain poorly understood, but devastatingly effective. When exposed to ultraviolet radiation, which bombards the Martian surface constantly, Due to the thin atmosphere and lack of protective magnetic field, perchlorates break down into highly reactive chlorine radicals. These radicals attack the carbon-hydrogen bonds in organic molecules with extraordinary efficiency, breaking apart even complex aromatic compounds that are normally considered stable over geological timescales. The Viking landers in 1976 had actually detected this destructive chemistry nearly 50 years earlier, but the scientific community misinterpreted the results. The Viking gas chromatograph mass spectrometer experiments showed that when Martian soil was heated, it produced chlorinated organic compounds. For decades, researchers assumed this meant the instruments had contaminated the samples. The new analysis reveals a more disturbing truth. The Viking landers had heated perchlorate-rich soil, causing it to combust any organic molecules present and produce the chlorinated compounds as decomposition products. We had detected the smoking gun of organic destruction, but mistook it for instrumental artifact. The temperature dependence of perchlorate decomposition on Mars creates what researchers now call the thermal paradox. Perchlorates remain relatively stable at the frigid Martian surface temperatures averaging -63 degrees Celsius, but become increasingly reactive as temperatures rise. This means that any geological process that might warm Martian rocks, volcanic activity, impact events, or subsurface hydrothermal systems, would simultaneously trigger accelerated organic destruction. The very conditions that might support life's chemistry also activate the planet's molecular-scale sterilization system. Curiosity rover's sample analysis at Mars, SAM, instrument, detected chlorobenzene and dichloroalkanes in samples from Gale Crater in 2013. At the time, CHIS researchers celebrated these findings as potential evidence of Martian organic chemistry. The devastating realization that emerged from the new Perseverance data is that these chlorinated compounds are not Martian organics. They are the cremated remains of whatever organic molecules once existed, transformed into chlorinated ash by reaction with perchlorates. We had been celebrating the evidence of life's destruction while believing we were finding signs of its preservation. The distribution of perchlorate concentrations correlates precisely with the locations where ancient water once flowed on Mars. Orbital imagery had identified Jezero Crater as an ancient lake bed with clear evidence of river delta deposits, making it a prime target for biosignature detection. The cruel irony revealed by the new data is that these water-rich environments, the exact locations where life would most likely have emerged, are also where perchlorate formation processes operated most efficiently. Water itself appears to have catalyzed the production of the very chemicals that would later destroy any biological evidence. The formation mechanism for such high perchlorate concentrations requires atmospheric chemistry operating over billions of years. Ultraviolet photolysis of atmospheric carbon dioxide in the presence of chlorine-containing minerals produces chlorine dioxide, which then reacts with mineral surfaces to form perchlorates. This process has been occurring since Mars lost its protective magnetic field approximately 4.2 billion years ago, creating a cumulative buildup of oxidizing compounds that permeates the entire upper crust of the planet to depths exceeding 5 meters. The magnetic field loss that allowed perchlorate formation represents the original catastrophe that doomed Mars. Approximately 4.2 billion years ago, Mars's liquid iron core solidified or developed circulation patterns that shut down the planet's magnetic dynamo. Within 500 million years, a geological instant, the solar wind had stripped away most of the Martian atmosphere, reducing surface pressure from potentially Earth-like conditions to less than 1% of Earth's current atmospheric pressure. This atmospheric loss exposed the surface to intense ultraviolet radiation that initiated the perchlorate formation cycle. The timeline of atmospheric loss coincides devastatingly with the period when life might have been emerging on Mars. Evidence from Martian meteorites suggests that liquid water existed on the surface until approximately 3.7 billion years ago. This overlaps with the period when life first appeared on Earth, suggesting that Mars and Earth may have had simultaneous opportunities for abiogenesis. However, Mars's perchlorate accumulation began just as these opportunities were emerging, creating a narrowing window of biological possibility. that may have closed before life could establish a permanent foothold. The oxygen isotope ratios in Martian meteorites reveal that Mars once had a much thicker atmosphere with significant water vapor content. So the deuterium to hydrogen ratio in what little atmospheric water remains is approximately 5.5 times higher than on Earth, indicating that Mars has lost the equivalent of a global ocean, at least 100 meters deep. The devastating implication is that this water didn't just evaporate into space. It reacted with surface minerals to form clays, sulfates, and perchlorates, locking away the very resource that life requires while simultaneously producing chemicals that destroy organic molecules. The clay minerals detected by orbital spectrometers across ancient Martian terrain were initially celebrated as evidence of past habitable environments. Clays form in the presence of liquid water at pH levels compatible with life, and their detection suggested Mars once had lakes, rivers, and possibly oceans where biological chemistry could have flourished. The new understanding reveals these clays as geological tombstones, marking where water existed long enough to form minerals, but not long enough to support sustained biological evolution before perchlorate accumulation rendered the environment lethally hostile. The jarosite minerals detected by the Opportunity rover in 2004 provided the first hints of the acidic, oxidizing conditions that now appear to be global. Jarosite forms only in highly acidic, iron-rich, sulfate-saturated waters, conditions fundamentally hostile to most terrestrial life. The presence of jarosite in multiple locations across Mars indicates that even during the period when liquid water existed, the chemical environment may have been far too extreme for biological chemistry, similar to what emerged on Earth. The subsurface radar data from the Mars Express Marsis instrument revealed layers of material extending to depths of several kilometers beneath the Martian surface. Initial interpretations suggested these might be sedimentary deposits from ancient oceans or lakes, potentially preserving biosignatures beneath protective layers of rock. The cruel reality emerging from chemical analysis is that these subsurface layers show the same exponential increase in perchlorate concentration with depth observed in Perseverance drilling samples. There is no safe depth, no protected reservoir, where organic chemistry might have survived intact. The seasonal methane variations detected by Curiosity rover between 2012 and 2017 had rekindled hope for subsurface biological activity. Background methane levels averaged 0.69 parts per billion, but periodic spikes reached 7 parts per billion, variations that some researchers interpreted as possible metabolic signatures from subsurface microorganisms. The devastating alternative explanation is that these methane pulses result from thermal decomposition of organic molecules in perchlorate-rich subsurface materials, representing not the breath of Martian life, but the last gasps of long-dead organic chemistry finally being oxidized to its simplest form. The carbon isotope ratios in the detected methane show values of delta C13 ranging from -25 to -48 per mil, encompassing the range produced by both biological and geological processes on Earth. This ambiguity, once seen as leaving room for biological interpretation, now appears more sinister. The wide variation suggests multiple carbon sources being thermally processed and released, consistent with the destruction of diverse organic materials accumulated over billions of years. We may be detecting the isotopic signature of an entire biosphere being slowly cremated by subsurface chemistry. The sample analysis at Mars Instrument detected organic molecules in multiple drilling locations within Gale Crater, with concentrations ranging from 10 to 10,000 parts per billion. Chlorobenzene, thiophanes, and other complex organics were identified, generating headlines about Mars's organic chemistry. The devastating realization is that these molecules shouldn't exist in their detected forms on Mars. They represent either contaminants from Earth or, more disturbingly, the partially degraded remains of much more complex organic assemblages that have been systematically dismantled by perchlorate chemistry over geological timescales. The depth profile of organic molecule detection shows a pattern exactly opposite to what would be expected if life had once existed on Mars. On Earth, organic concentrations generally increase with depth, as burial protects molecules from oxidative degradation. On Mars, organic molecule concentrations decrease with depth, according to the same exponential function that describes perchlorate concentration increases. This inverse relationship demonstrates that organics are being actively destroyed faster than they accumulate, with deeper, more ancient materials showing more complete oxidation. The thermal emissions spectrometer on Mars Global Surveyor mapped hematite concentrations across the Martian surface in the late 1990s. Hematite, a gray crystalline form of iron oxide, requires liquid water to form, and its detection was celebrated as evidence of past aqueous environments. The disturbing context now emerging is that hematite formation consumes oxygen from water molecules, contributing to the oxidizing environment while simultaneously removing the hydrogen that might otherwise react with carbon dioxide to form organic molecules. Even the mineralogical evidence of past water reveals processes that would have actively hindered organic chemistry. The recurring slope lineae, dark streaks that appear seasonally on Martian slopes, were initially interpreted as evidence of liquid water flowing on modern Mars. Spectrographic analysis showed hydrated perchlorate salts associated with these features, and researchers proposed that perchlorate brines might provide liquid water environments where microbial life could persist even under current Martian conditions. The devastating reality is that perchlorate brines are among the most hostile aqueous environments possible for life. The salts lower the freezing point of water, but they simultaneously create solutions so oxidizing that they would destroy cellular membranes and denature proteins within hours. The Phoenix lander conducted the first direct wet chemistry analysis of Martian soil in 2008, revealing a pH of 7.7, slightly alkaline, and seemingly compatible with life. This measurement generated optimism that at least some Martian environments might be chemically benign. However, the presence of perchlorates at concentrations exceeding 0.6% by weight means that any liquid water forming in these soils would immediately dissolve the perchlorates, creating solutions with oxidation, reduction potentials exceeding plus 1,000 millivolts. For comparison, most terrestrial bacteria cannot survive oxidation potentials above plus 500 millivolts. The radiation environment at the Martian surface represents an additional sterilization mechanism, working synergistically with perchlorate chemistry. The Radiation Assessment Detector on Curiosity measured surface radiation doses of 76 milligrays per year, approximately 40 times higher than radiation exposure on Earth's surface. This radiation flux breaks chemical bonds in organic molecules directly while also generating secondary free radicals that propagate oxidative damage. The combination of radiation-induced damage and perchlorate-mediated oxidation creates a double mechanism, ensuring organic destruction. The galactic cosmic ray flux penetrating to the Martian surface includes heavy ions with energies exceeding 1 gigaelectron volt. These particles create ionization tracks through materials, breaking chemical bonds and generating reactive species along paths extending several centimeters into rocks and soil. Modeling of the cumulative radiation dose over Mars's history suggests that the top 5 meters of the Martian surface has received sufficient radiation to completely sterilize any organic materials thousands of times over, even without considering chemical oxidation. The lack of a protective ozone layer on Mars allows ultraviolet radiation in the 200 to 300 nanometer wavelength range to reach the surface with intensities 30 times higher than on Earth. This UV flux is energetic enough to directly break carbon-carbon and carbon-hydrogen bonds in organic molecules. Laboratory experiments simulating Martian UV exposure show that complex organics like amino acids and nucleobases degrade to simple molecules within weeks of exposure. Timescales utterly insignificant compared to the billions of years these materials would need to survive to be detected today. The synergistic interaction between UV radiation and perchlorates creates a destruction mechanism far more efficient than either process alone. See, UV photolysis of perchlorates generates reactive chlorine and oxygen radicals that then attack nearby organic molecules. These radicals have diffusion ranges of several micrometers in Martian soil, allowing them to oxidize organics even in pore spaces, nominally shielded from direct UV exposure. The coupling of radiation and chemistry creates a sterilization zone extending several millimeters into the subsurface, far deeper than UV alone could penetrate. The timescale for complete organic destruction under current Martian conditions has been calculated at less than 5,000 years for surface materials. This represents one of the most devastating findings in the entire analysis. Even if life existed on Mars as recently as the dawn of human civilization on Earth, no detectable organic signature would remain at or near the surface. The search for ancient Martian life requires accessing materials deposited and then immediately sealed from atmospheric contact, a geological scenario that may be extraordinarily rare. The ExoMars Trace Gas Orbiter failed to detect methane in 2018 despite Curiosity's previous detections, creating what researchers call the methane paradox. The orbiter's sensitivity of 50 parts per trillion should easily detect the plumes Curiosity measured, yet observations from orbit showed no methane whatsoever. The resolution to this paradox appears to be that methane on Mars is destroyed so rapidly in the atmosphere that it never reaches detectable concentrations at orbital altitudes. Hydroxyl radicals produced by UV photolysis of water vapor oxidize methane with half-lives measured in hours rather than years, preventing accumulation even if subsurface sources continuously release the gas. The atmospheric photochemistry models, revised after the ExoMars null detection, show that Mars's atmosphere functions as an oxidizing reactor, destroying reduced gases far more efficiently than Earth's atmosphere. The combination of high UV flux, low atmospheric pressure, and the presence of oxidizing dust particles creates conditions where any organic molecule entering the atmosphere is systematically dismantled to carbon dioxide and water within days. This atmospheric cleansing system ensures that even continuous subsurface organic production could never create detectable atmospheric signatures. The dust devils and global dust storms that periodically engulf Mars distribute perchlorate-contaminated dust across the entire planet. Analysis of dust deposition rates suggests that the top centimeter of the Martian surface is completely replaced every million years through aeolian processes. This constant mixing ensures that even if localized regions somehow avoided perchlorate formation, they would be contaminated by wind-blown dust within geological timescales measured in mere millions of years, the blink of an eye compared to Mars's 4.6 billion-year history. The global dust storm of 2018 demonstrated the efficiency of Martian atmospheric mixing. Within 6 weeks, dust that originated in specific regions had been distributed across both hemispheres and all latitudes, creating a planet-encircling cloud. Optical depth measurements during the storm exceeded 8, meaning that sunlight had to penetrate 8 atmospheres worth of dust to reach the surface. And this dust carried perchlorates, oxidizing minerals, and UV-activated photocatalysts to every square meter of the Martian surface, ensuring chemical homogenization on planetary scales. The Opportunity rover's final resting place in Perseverance Valley provides a grim metaphor for Mars's hostility to both machines and potential biology. The 2018 global dust storm that ended Opportunity's mission deposited millimeters of perchlorate-rich dust over the solar panels, cutting off power. If the rover had been a Martian microorganism instead of a robot, the same dust would have delivered oxidizing compounds directly to its surface, ensuring destruction of any exposed organic chemistry. The planet that killed Opportunity operates through the same mechanisms that would kill any life attempting to exist there. The methane detection by the Planetary Fourier Spectrometer on Mars Express in 2003 to 2004 showed concentrations of 10 parts per billion in specific regions. This detection predated Curiosity's measurements and suggested localized methane sources that could indicate subsurface biology. The devastating counter-interpretation is that these methane plumes represent outgassing from impact-fractured crust, where ancient organic materials are being exposed to oxidizing conditions for the first time in billions of years. We may be detecting the planetary-scale cremation of Mars's last protected organic reservoirs. The crater formation rate on Mars ensures that the upper crust is completely overturned every billion years through impact gardening. Meteorite impacts excavate material from depth, exposing it to the oxidizing surface environment while simultaneously burying surface materials. This geological churning prevents the existence of permanently sealed repositories, where organics might survive intact. Even materials deposited in apparently protected environments will eventually be exhumed and destroyed by impact processes operating over geological time. The size-frequency distribution of Martian craters shows that impacts delivering more than 10 to the power of 23 joules of energy occur approximately every million years. These energetic impacts generate heat sufficient to vaporize perchlorates within hundreds of meters of the impact site, creating enormous clouds of reactive chlorine and oxygen species that rain down across thousands of square kilometers. Each major impact functions as a sterilization event, ensuring that even if life somehow survived in the aftermath of previous impacts, recurring bombardment prevents long-term biological continuity. The ancient heavy bombardment period that occurred approximately 4.1 to 3.8 billion years ago subjected Mars to impacts far more frequent and energetic than current rates. Basin-forming impacts like those that created Hellas, Arger, and Isidis delivered energies exceeding 10 to the power of 26 joules, sufficient to melt the crust to depths of tens of kilometers and eject material completely off the planet. If life existed during this period, it would have been repeatedly sterilized and forced to re-emerge from whatever protected niches might have survived, a cycle of destruction and potential re-emergence that may have ultimately exhausted the planet's biological potential. As the Martian meteorites that have fallen to Earth provide samples of Mars that have been naturally delivered for laboratory analysis. These meteorites show shock features indicating ejection velocities exceeding 5 kilometers per second, achieved through impacts energetic enough to heat the rocks to temperatures exceeding 1,000 degrees Celsius. Any organic molecules present in these samples would have been destroyed during ejection, explaining why Martian meteorites show virtually no indigenous organic content, despite coming from a planet where water once flowed. The ALH 84001 meteorite, discovered in Antarctica in 1984, generated enormous excitement in 1996, when researchers announced possible evidence of fossilized Martian bacteria. The carbonate globules, magnetite crystals, and worm-like structures were interpreted as biosignatures. The subsequent decades of analysis have systematically dismantled these claims, showing that all features can be produced by non-biological processes. The controversial structures now appear to be artifacts of sample preparation or products of shock metamorphism during impact ejection, the final disappointment in a long series of deflated hopes for Martian life. The organic molecules detected in ALH 84001 were initially measured at 50 to 100 parts per million, but subsequent analysis showed these to be terrestrial contamination acquired during the meteorite's 13,000-year residence in Antarctic ice. When contamination is accounted for, the indigenous Martian organic content of ALH 84001 is below detection limits, less than 1 part per million. And this represents exactly what would be expected for material that formed 4 billion years ago and has been exposed to Martian surface conditions, complete organic destruction. The carbonate minerals in ALH 84001 precipitated from water at temperatures below 150 degrees Celsius, according to oxygen isotope thermometry. These temperatures are potentially compatible with life, but the carbonate formation occurred approximately 3.9 billion years ago, during or shortly after the heavy bombardment period. The cruel timing suggests that by the time conditions stabilized enough for minerals to precipitate from liquid water, the bombardment and atmospheric loss had already created the oxidizing conditions that would prevent life from establishing a foothold. The lack of carbonate deposits in most Martian surface materials represents another devastating blow to biological optimism. On Earth, carbonate rocks like limestone are primarily produced through biological processes, with marine organisms extracting dissolved carbon dioxide to build shells and skeletons. The near absence of carbonates on Mars, despite clear evidence of past liquid water, suggests either that water persisted for insufficient time for carbonates to accumulate, or that the water chemistry was too acidic for carbonate precipitation, both scenarios hostile to life's emergence. The sulfate deposits detected across Mars by orbital spectrometers indicate that when liquid water existed, it was often acidic and sulfur-rich. Sulfate minerals like gypsum and kieserite form in evaporating acidic waters, suggesting that Martian surface waters may have had pH values between 2 and 4, similar to battery acid. While some terrestrial extremophiles can survive such conditions, these organisms evolved from ancestors that developed in more benign environments. The emergence of life directly in such hostile chemistry appears far less probable than adaptation to acidity after life is already established. The spectral signatures of phyllosilicate clays detected in ancient Martian terrains indicate formation in neutral to slightly alkaline water, conditions more favorable for life than the acidic sulfate environments. However, the clay-bearing units are predominantly found in the most ancient terrains dating to the Noachian period more than 3.7 billion years ago. By the time the Hesperian period began around 3.7 billion years ago, the geological record shows a transition to sulfate deposition, indicating environmental degradation from potentially habitable to decisively hostile. If life emerged during the Noachian, it would have faced increasingly lethal conditions as Mars's chemistry evolved toward its current oxidizing state. The dichotomy between Mars's northern lowlands and southern highlands represents the most prominent geological feature on the planet. The northern hemisphere sits 5 to 6 kilometers lower than the southern hemisphere, and some researchers have proposed that this lowland once hosted an ocean covering approximately 1/3 of the planet. However, the lack of definitive shoreline features and the absence of evaporate deposits expected from ocean evaporation suggest this ocean, if it existed, was short-lived on geological timescales, perhaps mere millions of years, rather than the hundreds of millions or billions of years that would be required for life to emerge and evolve to detectable complexity. The valley networks that dissect ancient Martian highlands resemble terrestrial river systems, indicating that liquid water once flowed across the surface. However, detailed analysis of valley morphology shows characteristics inconsistent with long-term fluvial activity. Most Martian valleys lack the tributary development and meandering patterns seen in terrestrial river systems that operate over millions of years. The morphology suggests episodic flooding rather than sustained flow, brief intervals of water release, lasting perhaps decades to centuries, separated by millions of years of aridity. These flood episodes would provide insufficient time for life to establish stable ecosystems. The equilibrium temperature of liquid water under ancient Martian atmospheric conditions presents a fundamental problem for sustained habitability. Climate models incorporating realistic solar luminosity for the young sun show that even with a thick carbon dioxide atmosphere, surface temperatures would have averaged well below freezing. Liquid water could exist only during transient warming episodes triggered by volcanic eruptions, impacts, or orbital variations. Temporary greenhouse events lasting thousands to tens of thousands of years before refreezing occurred. Life emerging during these warm intervals would face extinction during the subsequent freeze, unless it could survive in subsurface refugia. The carbonate-silicate cycle that maintains Earth's climate stability over geological time appears to have failed on Mars early in its history. On Earth, this cycle sequesters atmospheric carbon dioxide in carbonate rocks during warm periods and releases it through volcanic outgassing during cold periods, creating a thermostat that maintains habitable temperatures. The lack of plate tectonics on Mars prevented efficient recycling of carbonates back into the mantle, allowing atmospheric carbon dioxide to be permanently locked away in rocks and minerals. Without this climate regulation, Mars entered a runaway cooling scenario that made long-term habitability impossible. The loss of Mars's magnetic field, approximately 4.2 billion years ago, represents the ultimate catastrophe that sealed the planet's fate. The magnetic field had protected the atmosphere from solar wind erosion, maintained higher atmospheric pressure that allowed liquid water stability, and shielded the surface from radiation that drives perchlorate formation. The field's collapse initiated a cascade of interconnected failures: atmospheric loss, water loss, temperature decline, radiation increase, and perchlorate accumulation. This cascade transformed Mars from a potentially habitable world into a molecular-scale incinerator within several hundred million years. The evidence for magnetic field loss comes from the remnant magnetization preserved in ancient crustal rocks. Orbital magnetometer measurements show that terrains older than 4.1 billion years retain strong magnetization, indicating they formed while a global magnetic field still existed, while younger terrains show no magnetization, demonstrating that the field had ceased by the time these rocks solidified. This geological record provides precise timing for the beginning of Mars's transformation from possibly habitable to certainly hostile. The rate of atmospheric loss after magnetic field collapse has been directly measured by NASA's MAVEN mission. Observations show that Mars currently loses approximately 100 grams of atmosphere per second to solar wind stripping. Extrapolating this rate backward through time, accounting for higher solar wind intensity in the early solar system, suggests that Mars lost the equivalent of a 1-bar atmosphere, similar to Earth's current atmospheric pressure, within 500 million years of magnetic field collapse. This rapid atmospheric depletion prevented the long-term climate stability required for life to emerge and evolve. The crustal dichotomy may itself be related to the magnetic field loss through a catastrophic impact scenario. Some researchers propose that a massive impact in the northern hemisphere disrupted mantle convection patterns, shutting down the dynamo that generated the magnetic field. If correct, this scenario means that a single random event, a catastrophic impact during the heavy bombardment, may have determined Mars's entire subsequent history, foreclosing any possibility of long-term habitability through sheer bad luck, rather than any inherent planetary inadequacy. The comparison between Mars and Earth illuminates how narrowly constrained the conditions for life's emergence and persistence may be. Earth and Mars formed from similar materials at similar times in similar regions of the solar system. Both had liquid water on their surfaces during their first billion years. Yet Earth developed a rich biosphere that has persisted for at least 3.5 billion years, while Mars appears to have remained sterile or lost any life that briefly emerged. The divergent outcomes suggest that sustaining life requires not just initial favorable conditions, but continuous maintenance of those conditions over geological time, a requirement Mars failed to meet. The nitrogen budget of Mars represents another limiting factor for biological potential. Life on Earth requires nitrogen for amino acids, nucleotides, and numerous metabolites. Mars's atmosphere is only 2.6% nitrogen compared to Earth's 78%, and this nitrogen exists primarily as chemically inert N2 molecules. The lack of nitrogen-fixing mechanisms in the absence of life creates a chicken and egg problem. Life needs fixed nitrogen, but fixing nitrogen efficiently requires biological catalysis. The marginal nitrogen availability on Mars may have prevented the accumulation of nitrogenous compounds necessary for life's emergence. The phosphorus availability on Mars presents yet another biochemical constraint. Phosphorus is essential for DNA, RNA, ATP, and phospholipid membranes. No known form of life can exist without it. While Mars has phosphorus-bearing minerals, the oxidizing, acidic conditions that prevailed when liquid water existed would have kept phosphorus locked in insoluble minerals rather than dissolved in bioavailable forms. Laboratory experiments simulating Martian water chemistry show that phosphorus concentrations would have been 1,000 times lower than required for the emergence of phosphorus-based biochemistry. The energy sources available for life on early Mars appear insufficient to support robust biospheres. On Earth, photosynthesis powers most ecosystems, but early Mars's thicker atmosphere would have absorbed more sunlight than Earth's. reducing the energy available for photosynthetic organisms. Chemical energy from hydrothermal systems could theoretically support chemosynthetic life, but the volcanic activity required to maintain such systems appears to have declined rapidly as Mars's interior cooled. By 3.5 billion years ago, volcanic resurfacing had essentially ceased, eliminating these alternative energy sources. The rapid cooling of Mars's interior resulted from the planet's smaller size compared to Earth. With only 11% of Earth's mass, Mars has a higher surface area to volume ratio, causing more rapid heat loss. This accelerated cooling solidified the mantle, shutting down volcanic activity and plate tectonics within the first billion years of the planet's history. Without the geological activity that recycles nutrients, provides chemical energy sources, and maintains atmospheric composition, any biosphere that emerged would have faced resource depletion and extinction, even without the oxidizing chemistry that developed later. The absence of plate tectonics on Mars prevented the development of the complex geochemical cycling that makes Earth habitable. Plate tectonics subducts oceanic crust, melts it in the mantle, and returns materials to the surface through volcanism, creating cycles that distribute nutrients and maintain atmospheric composition. Mars's stagnant lid tectonics locked materials at the surface, preventing recycling. The resulting geological stasis would have concentrated certain elements while depleting others, creating geochemical imbalances incompatible with sustained biological activity. The search for Martian life may have been fundamentally misconceived from its inception. Scientists designed instruments and selected landing sites based on the assumption that Martian life, if it existed, would resemble terrestrial life. Carbon-based, water-dependent, leaving organic signatures detectable through mass spectrometry and chromatography. However, then if life emerged on Mars and then evolved under increasingly hostile oxidizing conditions, it might have developed biochemistry radically different from terrestrial life, perhaps based on different elements, using different solvents, or employing completely different molecular mechanisms. Our instruments, optimized for terrestrial-type biosignatures, would overlook such alternative biochemistry entirely. The possibility of weird life on Mars, operating through non-carbon chemistry, has received minimal serious investigation. Silicon-based life, nitrogen-based life, or metabolic systems using sulfuric acid rather than water remain in the realm of speculation rather than systematic scientific search. The bias toward carbon-water biochemistry reflects our single example of life, the terrestrial biosphere, but may blind us to alternative possibilities that could exist under Martian conditions. This anthropocentric bias may have caused us to search for the wrong signatures in the wrong locations. The perchlorates that doom carbon-based organic chemistry might paradoxically provide energy sources for hypothetical perchlorate metabolizing life. Some terrestrial bacteria can use perchlorates as electron acceptors in their metabolism, gaining energy from perchlorate reduction coupled to oxidation of organic compounds. If Martian life evolved mechanisms to safely harvest energy from perchlorate reduction rather than being destroyed by perchlorate oxidation, it could exploit the very chemical conditions that appear hostile to terrestrial biochemistry. However, no evidence for such metabolism has been detected, and the energetics of perchlorate reduction under Martian conditions remain marginal for supporting active metabolism. The recurring slope lineae that appear seasonally on Martian slopes were initially celebrated as possible habitats for perchlorate metabolizing microorganisms. The combination of liquid brine and high perchlorate concentrations seem to offer both solvent and metabolic substrate. However, laboratory studies of terrestrial perchlorate-reducing bacteria show that these organisms cannot survive in solutions with perchlorate concentrations exceeding 10% by weight, far below the saturated brines required to remain liquid at Martian temperatures. And the environmental conditions in recurring slope lineae appear too extreme, even for extremophiles evolved specifically to tolerate perchlorates. The detection limit of current life detection instruments represents a critical threshold that Mars may fall below. The sample analysis at Mars instrument on Curiosity can detect organic molecules at concentrations above approximately 1 part per billion. If Martian life exists but maintains biomass densities 1,000 times lower than terrestrial soil microorganisms, it would produce organic signals below SAM's detection threshold. We may be concluding Mars is sterile, not because life is absent, but because it exists in such sparse populations that our instruments cannot detect it, a possibility that provides cold comfort since such marginal biospheres would be scientifically undetectable with current technology. The subsurface habitability models suggest that if life exists on Mars, it must reside at depths of hundreds of meters to kilometers below the surface. At these depths, geothermal heat maintains temperatures above freezing, radiation is attenuated to survivable levels, and liquid water might exist in pore spaces. However, accessing these depths for sampling remains far beyond current technological capabilities. The deepest drill attempted on Mars penetrated only 7 centimeters before encountering mechanical difficulties. Reaching the depths where life might survive would require drilling capabilities, orders of magnitude, beyond what has been deployed. The energetic cost of drilling to habitable depths on Mars with robotic systems presents staggering engineering challenges. Each meter of drilling in hard Martian rock requires hundreds of watts of power sustained for hours, energy levels far exceeding what solar panels can provide at Martian distances from the sun. Nuclear power sources could provide sufficient energy, but the mass of drilling equipment, power systems, and sample analysis instruments required for deep subsurface investigation would necessitate missions costing tens of billions of dollars, politically unfeasible in the current funding environment. The Sample Return Mission plan for the 2030s represents humanity's best near-term hope for definitively resolving Mars's biological status. By returning Martian samples to Earth laboratories, scientists can apply analytical techniques thousands of times more sensitive than instruments that can be sent to Mars. However, even sample return faces the devastating reality that surface samples will have been sterilized by perchlorate chemistry and radiation. Unless the sample collection strategy specifically targets freshly exposed subsurface materials, the returned samples may simply confirm what we already know. The Martian surface is a molecular graveyard. The planetary protection protocols designed to prevent contamination of Mars with terrestrial life now seem tragically ironic. Spacecraft sent to Mars undergo extensive sterilization to ensure they carry fewer than 300,000 bacterial spores, with specific components limited to 300 spores. These protocols assume Mars might harbor indigenous life that could be disrupted or overwhelmed by terrestrial contamination. The new understanding of Martian chemistry suggests these protocols are unnecessary. Mars's perchlorates and radiation will sterilize any terrestrial contamination within years of arrival, just as they have sterilized any indigenous Martian organics. The ethical implications of terraforming Mars have been debated for decades, under the assumption that Mars might harbor indigenous life that would be displaced or destroyed by human modification of the planet. The discovery that Mars is likely sterile and has been for billions of years removes this ethical constraint. If no Martian biosphere exists to protect, the moral argument against terraforming collapses, leaving only practical and economic considerations. This realization may accelerate plans for human colonization and planetary engineering by eliminating the bioethical objections that previously complicated such proposals. The technical feasibility of terraforming Mars appears more daunting than optimistic scenarios suggested. Proposals to warm Mars by releasing greenhouse gases, melt polar ice, and create a thicker atmosphere fail to address the fundamental problem. Without a magnetic field, any atmosphere created will be stripped away by the solar wind within millions of years. Creating and maintaining a habitable Mars would require either restarting the magnetic dynamo, far beyond current technological capabilities, or constructing a magnetic shield at the Mars-Sun-L1 point, a mega project requiring resources and capabilities that may remain science fiction for centuries. The comparison with Venus illuminates alternative planetary fates and the narrow range of conditions that permit habitability. Venus may have once had liquid water oceans similar to Earth, But a runaway greenhouse effect boiled away the oceans and created a surface temperature of 462 degrees Celsius under a crushing 92-bar atmosphere. Mars followed the opposite trajectory: atmospheric loss, cooling, and desiccation. And Earth, alone among the 3 rocky planets in the habitable zone, maintained the delicate balance required for sustained liquid water. A balance so precarious that the emergence of life on Earth may represent extraordinary luck rather than an expected outcome. The anthropic selection effect complicates our ability to assess the probability of life emerging on planets like Mars. We exist on Earth precisely because Earth's conditions allowed life to emerge and persist. We cannot observe the vast majority of sterile planets because no observers evolved there to make observations. This selection bias means we cannot reliably estimate how common or rare habitable planets are based solely on Earth's example. Mars provides our only opportunity to test whether Earth-like conditions reliably produce life, or whether Earth represents an improbable exception. The null result from Mars carries profound implications for the search for extraterrestrial intelligence. If life failed to emerge on Mars, despite billions of years with liquid water, similar atmospheric composition, and geological activity comparable to early Earth, this suggests the transition from chemistry to biology may be extraordinarily improbable. If abiogenesis requires conditions even more finely tuned than those that existed on early Mars, the number of planets hosting life in our galaxy may be far smaller than optimistic estimates of millions or billions of inhabited worlds.